Good morning everybody. Let us today start the basic of nuclear magnetic resonance. What is meant by nuclear magnetic resonance? The fundamentals let us discuss. Now, as the name nuclear, it deals on the properties of the nucleus. Hence nuclear. Magnetic, it consists of the magnetic property of the nucleus, and what is resonance? It will be clear after the discussion. So let me first start what we mean by nuclear magnetic resonance. Now, all of you go through the atom, and inside the atom the core particle, the heavy particle is the nucleus, and the total mass of the atom is concentrated at the nucleus, and the nucleus contains some positive charge, these are known as proton, and some non-charged particle but having some mass are known as neutron. And due to the neutron and proton, the mass is concentrated in the nucleus. Now we are focusing on the nucleus. As we focusing on the property of the nucleus, next it starts with nuclear. Now what is nucleus? Already we have discussed, this is the core particle which has positive charge and situated at the core of the atom. Now, as it is positively charged particle, all charged particles have some spin. These are rotates along their axis like this. All charged particles moves around their axis, they spin, and due to this spin, they have some electric field and also some magnetic field. Now in this case, we consider the magnetic field of the nucleus. So due to the rotation of the charged particle, some magnetic field is generated, and this magnetic field is taken into consideration here. Now, all nucleus have no magnetic property. Only some nucleus have magnetic property, but not nucleus. How? Let us discuss. This is one table in front of you. Here, mass number, atomic number, spin quantum number of the nucleus, and examples. For example, if the mass number is odd and the atomic number either odd or even, then the spin quantum number I of the nucleus may be half, may be 3 by 2, may be 5 by 2. These are nothing but the half integers. And the examples are hydrogen with atomic number 1 and mass number 1. 1 is odd number, mass number 1 is odd number. And the magnetic spin quantum number I is half, it is a half integer. Now carbon 613, the atomic number is atomic mass is 13, this is odd, but the atomic number is 6, this is coming under even. And the spin quantum number is half, it is half integer. Another example is 817 oxygen. Another case, the mass number is even, the atomic number is even. At that time what happened? The spin quantum number I becomes 0. And the examples are carbon 612, both are even 612. It is coming 0, oxygen 816, both are even coming 0. Another case, mass number even, atomic number. At that time, the spin quantum number I may be 1, 2, 3 like these integers. Examples are hydrogen 1, 2, even, mass number even, atomic number odd, integer 1, nitrogen 17, 14, mass number is 14 even, atomic number 17 odd, and the integer is 1. So this type of nucleus, different type of nucleus having either odd or even mass number or atomic even or mass number, they are categorized in this way. Out of these, which have 0 spin quantum number, they have no magnetic property, and only these either having spin quantum number of half integers or spin quantum numbers of integers, they have only the nuclear property. So nucleus having odd mass number or odd atomic number, category 1. Category 2, either odd mass number or even atomic number, or even mass number or atomic number, only gives NMR spectra. So all nucleus does not give NMR spectra, but this type of nucleus which has some restricted property, they only give the nuclear spectrum. Now how they give the nuclear spectrum, let us discuss. Now let us consider the nucleus. which has the positive charge due to the proton, and this is the axis of rotation, and it rotates along its axis by circular motion, and due to this circular motion magnetic property will be there. So this is the nucleus having magnetic property. This is coming under any of this category, either half integer or integers. Now what happens? If one external magnetic field is applied to this is a tiny magnet, this nucleus is a tiny magnet. When one external magnetic field is applied, whatever the external magnetic field is applied from the downside, and this is the notation of the external magnetic field. At that time what happens? Due to the influence of the external magnetic field, it changes its magnetic field. There is the influence of the external magnetic field on this magnetic field. So due to this influence and due to restriction of some quantum number, it possesses some precessional motion. Now let me discuss what is a precessional motion. Let us take the example of a top. The rotating top, in this case, this is the vertical axis, and also the top is rotating along with the vertical axis, and this is also its axis of rotation. Now in this case, the vertical axis and the axis of rotation both are same. So in this way, the top is rotating along its own axis. Now what happens? When we apply the external magnetic field, it has two types of motion. Either the lower part may be deviated from the vertical axis. In this way, the top part is fixed, the lower part is deviated from the vertical axis, and it is rotated along the vertical axis. Or the lower part is fixed, the top part is deviated from the vertical axis, and these two types of motion will be there, and these two types of motion are known as precessional motion. Precessional motion is nothing but when the axis of rotation is deviated somewhat from the vertical axis. At that time, this type of circular motion are known as the precessional motion. Now, precessional motion is achieved due to the application of the external magnetic field. So, when external magnetic field is applied, at that time, our nucleus is also get precise. And when it precise, it has two types of orientation. Let me discuss. This is the direction for the magnetic field of the external magnetic field. Now what happens? This is the case. Now as this is precise in this manner, it is the upper part is rotated, and this is the force, and the resultant will be like this in this direction. And this is the top case, the resultant will be in this direction. Now see, the resultant of the precise nucleus, the direction of the magnetic field is towards the top, and at the same time the direction of the external magnetic field is also in the same direction. Now this is the case, both are parallel, and this case is known as aligned. So the magnetic field of the precise nucleus and the magnetic field of the external magnet are in same direction, hence it is known as parallel or aligned. Other cases, the direction of the magnetic field of the precise nucleus is just opposite to the external magnetic field, hence it is known as anti-parallel, or it is known as opposite. It opposes the magnetic field of the external magnetic field. When it is parallel or aligned, at that time it has low energy state, and when it is anti-parallel or opposed, it has high energy state. The low energy state is known as ground state, and the high energy state is known as excited state. So due to precessional motion, due to the application of the external magnetic field, our nucleus, which is a tiny magnet, now gets precise. Due to precessional motion, it has two types of orientation, either aligned with, or parallel with, or anti-parallel with, or opposed with, or it is also known as low energy state, it is high energy state, it is ground state, it is excited state.
Start.
Now this energy difference between the ground state and excited state is del E, energy difference. Now this energy difference comes in the range of radio frequency range. Radio frequency range. So the energy difference between the excited and ground state is the daily, and this energy difference fall in the region of radio frequency range. Why radio frequency range? I am telling you that. Now in this case, the ground state precessional nucleus, if got some energy, it will go to excited state. And when it radiates its energy, again it comes to its ground state. So, after gaining the energy, it moves from ground state to excited state. After losing the energy, it comes from excited state to ground state. And that energy difference is coming under radio frequency regime. So, in this case, what happens? If a suitable radio frequency operator is applied, at that time the range which is get same with this energy level, at that time one specific radiation of the specific frequency get absorbed, and when that absorption takes place, at that time there will be a peak in the NMR spectrum. There will be a peak in the NMR spectrum. So this is the basic fundamental of the nuclear magnetic resonance. Now we are focusing on the nuclear property. Which property of the nucleus? The magnetic property of the nucleus. Now what is resonance? So when the radio frequency of suitable frequency is get same with this energy difference, and at that time a particular energy of the radio frequency wave is get absorbed, and at that case the instrument give a peak in the NMR spectrum, and basic on that peak we can recognize what type of nucleus is there. So this is the fundamental of nuclear magnetic resonance, and I hope it is clear to you what is the meaning of nuclear magnetic resonance. In next class we will discuss about the basic principle of proton NMR or HNMR and C13 NMR. So thank you all.